First, I'd like to introduce our next speaker, Professor Yiping Zhao from University of Georgia. He's with the Department of Physics and Astronomy, Director of the Nanoscale Science and Engineering Center. His research focus is on nanofabrication using GLAD and DSG techniques. Does a lot of surface enhanced Raman spectroscopy, plasmonics, structure fabrication, and other interesting nanoscale and catalytic phenomena. So he's going to talk about, with the title, When Glancing Angle Deposition Meets with Colloidal Lithography. So Professor Zhao.
Thank you very much. Thank you, Park Scientific System actually invited me to give a talk over here. I want to shift the gear a little bit because essentially we are not working on semiconductor industry, and we are making some nanostructures and then play optical properties. So my postdoc actually recently made this nice cover actually showing the glance angle deposition together with the colloid. Our work essentially is based on so-called colloid lithography or natural sphere lithography or nanosphere lithography come together with glance angle deposition. So I'll give a very brief introduction of what is colloid lithography and also glance angle deposition. And there's two kinds of structures they can form. One is on the particles themselves, and also you can use the particle as a mask to deposit nanostructure. How we can utilize both of them actually to engineer some of those three-dimensional nanostructure that have specific optical property. So colloid lithography essentially is a very simple concept. It was coined like in 1982, the first paper published in APL. Essentially, you put monolayers of close-packed colloid, especially polystyrene beads or silica beads, right? You can use it as a mask, and then you can perform thermal evaporation or E-beam evaporation or spotting or whatever. And during the evaporation, you have thin film actually deposited not only on top of the spheres, also because there's a gap between adjacent sphere, right? You also use that as a template, so mask, so you can actually deposit material on top of the substrate. So you can either have the thin film on the sphere, or you can remove this colloid layers just using a very simple tape to peel it off, so that you can form nanostructured features over there. Usually, when people doing this colloid lithography, they just deposit thin films directly on top of the substrate. And if they can combine different kind of fabrication technique like etching or other lithography, actually you can make all kinds of structures like nanohole structures, nanotriangle pillars, and the domes, circles, and things like that. However, if we actually can change the deposition configuration a little bit for the thin film deposition, so this is so-called the dynamic shattering growth or glance angle deposition. So in a vapor deposition system, if this is the source, so you tilt the substrate at a very large angle. When vapor actually come down over here, there's a so-called shattering effect, right? So it's just like you dancing on the sun, you have the shattering. And once you have the shattering effect, the protrusions on the surface can receive more vapors compared to the shadow, right? So when you grow like this, and while you're growing and also rotate the substrate azimuthally, you can actually generate different kind of topological nanostructures on the surface. So this is a self-assembled process during the growth. So during the past 20 years, actually when I worked with Professor Wang's group, and then after I came to UGA, we actually made a lot of different kinds of nanostructures using glance angle deposition. For example, you can change the shape of the nanostructure. You can also do the multi-layer deposition so that you can get heterostructures. Also, you can do the co-deposition we did not show over here, so you can form a composite nanostructures in this way. So usually, when we use the colloid monolayers, we tend to use them as a template. So the shadow effect has so-called self-alignment effect. So when you have the colloid monolayers, they act as the seeds. So the growth nanostructure actually can align on top of the seeds, so you can see you can form a regular spacing nanostructure in this way. However, if we grow a very thin layers, and then we utilize the rotation and also the incident angle, we can design a very specific plasmonic nanostructures. So first, if we look at the structure deposited on the nanosphere, right, what kind of thing we can deposit? Now, when we prepare those colloid monolayers, nobody can get a perfect, large area, single domain structure. Usually, you have multiple domains. When you have multiple domains, it breaks symmetry when you have a tilted deposition, right? So here is an example of the preparation we have done. And here's an image shows that you have, this is big domain over here. It's another big domain. You have a small domain over here, right? So you have different orientations. Now, if we do a vapor deposition at a very large angle with respect to surface normal to this thing, right? So this is a top view. This is a cross section. From the cross section, you see you define this polar angle. From this top view, you define a azimuthal angle with respect to the center to center direction, baseline over here. So once you change the phi angle with fix the theta angle, what kind of pattern you think you can deposit onto this sphere? Because if the incident angle is very large, you don't have any deposition on top of the substrate. You only have a deposition on the sphere, right? So if we change the phi angle, for example, if phi equals 0, you actually get a very elongated strips on top of this sphere. However, if you keep on changing that, you can see that when phi is changing 1 degree at a time, the shape of these structures on top of that start to change. Now we can actually utilize this. We know that if we deposit silver, silver has so-called localized surface plasma resonance. Now if the structure is anisotropic, then it has a different LSPR mode, longitudinal and also vertically, perpendicular to that. So if you actually look at the property of those, we can utilize this kind of different shape to engineer a so-called broadband optical absorber. What I can do is that, for example, I have a sample. I don't know the orientation of each domains. I started at a phi angle. Supposedly, phi angle equals 0 degree. I first deposit a layer of silver and then cover that with a small thin layer of silicon dioxide. Then I start to rotate the whole thing 65 degrees. Now remember that this is a closed packed structure, so it has symmetry. Like every time you rotate 6 degrees, it essentially have the same phi angle. But if I rotate 65 degrees, that means effectively I rotate 5 degrees, right? So it changes the shape. Each domain changes the shape. Now next time, if I do 130 degrees, essentially, effectively I rotate 10 degrees. If doing so on like so on, so that means essentially I have a stacks of silver nanostructure with different shapes. Now if it's with different shapes, their LSPR peak actually start to shift. We did a FDDT simulation. So if the shape is like this, shape is like this, if you look at the absorbance spectrum, it has peak over here, peak over here, peak over here. So you actually can scan different kind of peak. When all this add together, essentially, you can see that the absorbance of the material on top of that, we have different layers. So n equals 1 to still 7 layers. We rotate all around 360 degrees. So you can see that seven layers for different diameter of nanosphere. We have a very flat absorbance, and the absorbance is almost more than 90% of the material. So you can use that way to simply design a broadband absorber in such a way. Now, since you can see that there's different shape, can we take the advantage of the shape and design something more? For example, if we look at this sphere over here, look at the shadowing at a very large angle. The least labor actually starts to shadow the gross vapor, right? So if we grow a silver, that only this part you will form a silver. If you look at the shape of this, it's like a fan, right? So if I rotate this substrate 120 degrees, I can grow a second fan over there. If I rotate another 120 degrees, I can grow a third one. If you look at the whole structure, it has a handless. It's like my right hand and my left hand. If you move like this way, they never overlap with each other. So if the structure have handless, that means if I use different light to interact with it, it will have different property. For example, this is a SEM picture of the fan structure. At that time, we don't have the Park AFM system yet, so we use SEM to look at the structure as like a fan. And so if we have, the light have also handless. So we can have, right-handed circular polarized light and the left-hand side circular polarized light, right? If the structure have handless, then their index refraction due to the right-handed polarized light and the left-handed polarized light will be different. Their absorption will be also different, right? So this is called circular birefringence. If the index refraction is different, or if the absorption is different, this is called circular dichroism. Actually, this was used for characterize those biologic samples. For example, like DNA, proteins, they always have handless, right? In nature, many, many molecules have handless. So if we actually use those circular polarized light to look at the structure, we can do, the structure like I can rotate clockwise, I can rotate counterclockwise. If you look at the delta T, which is the right-handed circular polarized light minus the left-hand circular polarized light transmission, you can see that, the delta T for the CCW is this response, and for the CW is exactly the opposite, right? So you can use that actually to design this is so-called chiral metamaterial or metasurface in such a way. But this is like a planar or quasi three-dimensional chiral metamaterial. Now, can we do something even more complicated than just two-dimensional or quasi three-dimensional structure? We can also utilize the same glance angle deposition principles. For example, I can first deposit a layer of silver in this direction, and then I can rotate the substrate and deposit onto the opposite direction a silicon dioxide layer. And then I rotate back 90 degrees, deposit another layer of silver, and then in the opposite direction, we can deposit silicon dioxide. If I keep on doing that, now what we get is helically stacked silver layers, right? So essentially, we have a three-dimensional handless structures in this way. So we can do clockwise. We can also do counterclockwise. So if we do, for example, a first layer of silver, you can see when phi equals 0, you have this strip structure. When phi equals 50 degrees, you have this little triangular structure like that. Now, if I do a three-layer silver, silicon dioxide silver, you can see there's an L-shaped kind of formation over here. This is a little L shape. If we did all the 7 layers over here, it forms like rectangular structures over here. This is our simulations using MATLAB. And then, if they have, this is a TEM image of one of the particles we look at there. So you can see over here is silver, the dark part. This light part is silicon dioxide. But it depends on the orientation of the structure. At different orientation, the structure looks different. The cross-section looks different. Essentially, you can see if we have different size of the particles, then their CD response is different. So this is a non-polarized transmission. You can see both left-hand sided, right-handed sided, they have almost exactly same non-polarized transmission response. However, if we look at the delta T, which is the circular polarized difference transmission, they are exactly opposite to each other, very nicely opposite to each other. And you can see that the peak of this CD, they shift as a function of the diameter of the spheres. So you can use that to tune the response of the CDs using these simple structures. Now, can we make an even more complicated 3D structure, right? Like switch row. Switch row is also a chiral structure, right? We can do that essentially very easily, also utilize glance angle deposition. And so first, what we do is that we're using glance angle deposition. We make a very small silicon dioxide terrace. Okay, so this is little protrusions of silicon dioxide on top of those spheres. Then we change the incident angle to a little smaller incident angle, and then we can grow silver. Now, during this grow, actually, we start to rotate back and forth, swing the substrate. Then we can put a layer of silver on top of that, right? Then on the other side, okay, we can put down silicon dioxide, and then we rotate back 90 degrees, and then we can keep on doing that, okay? Silver deposition and silicon dioxide deposition. So if I say, okay, this is first silver layers, then over the opposite direction, you deposit silicon dioxide. On the other 90 degree, deposit silver, and on the opposite direction, doing the silicon dioxide again. So if you look at the cross-section over here, if you keep on doing that, okay, if you look cross-section, essentially you get a switch row kind of structure of silver and also silicon dioxide. And this structure, we can do the left-hand side or right-hand side, they showed opposite response in terms of CD. And you can see that this CD is very broadband compared to the previous structure. Right? So this is a very simple way you can utilize glance angle deposition and the colloid monolayer to design three-dimensional plasmonic chiral structures. Obviously, you can design more if we have more ideas. Another one essentially is, okay, the nanostructure on the substrate. Like usually, okay, when we grow those structure on substrate, we use flat substrate, right? How about, okay, if we have the monolayers on a curved substrate? So we can use, nowadays, we can use a 3D printer, okay, to make a curved block over here. And then you can put down monolayers, for example, first onto a polystyrene, PDMS, okay, thin film strip, and then tape that onto, okay, the curved structure over here. So you can do the convex surface, concave surface, and then if we have a vapor come down in this way, because at different locations the relative incident angle is different, then the size of the triangle you're going to form on the substrate will be different. So you'll have a series of, okay, different size of triangle. Now, if this is a triangle is made by silver or gold, then they should have different optical properties. Then it should show different colors. For example, we have different diameters of those block. So this is a PDMS. If we peel off this colloid, you can see there's different colors. It's not very clear. So from the center to the end, this is a bluish. To the end is the reddish. And this is the SEM picture. This is the AFM picture. At that time, we get the Parkes AFM system. So you can see that the triangle actually, okay, at different locations start to become smaller and smaller and smaller. Now, if we scan the optical property, like their absorbance from the center to the edge, we can see that in the center you have a very sharp pronounced LSPR peak, and with the increase of the location, this peak actually starts to blue shifted, which, okay, because the size of the particle becomes smaller, essentially, okay, the absorption peak actually blue shifted. That is correspond to the LSPR principles. Obviously, okay, not only you can just do a single deposition, during the deposition you can also rotate the substrate, right? So when we rotate the substrate with the colloid over here, essentially if the incident angle is 0 degree, you get this traditional triangle shape of nanostructures. Now if the incident angle changes from, okay, 0 degree to 10 degree or 15 degree, the shape of the structure starts to change. Now if the shape of the structure, for example, this is a experimental realization of the silver structure, you have individual triangles, then you have this kind of multi-side structures. Then when the angle becomes larger and larger, all those nanostructures actually connect together. It becomes a network. So those structures, if we can tune, for example, the gap between all those particles. Essentially, that's very good for surface enhanced Raman scattering or other things like for plasmonic applications. For example, you can see that the extinction spectrum actually changed with the incident angle. You can find a relationship between, okay, how the peak change as a function of the deposition angle when you rotate the substrate. Another way is that we don't necessarily have to use the close-packed colloid layer as the template, right? We can etch the template. So if we actually etch those colloid, then make gaps in between, and then if you deposit at different incident angle, like one is this direction, then you rotate 120 degrees this direction, another 120 degrees this direction, then essentially not only you have deposition on top of the beads, you also have deposition on the substrate. Now then you can form even more complicated pattern onto the substrate. Depend on the initial alignment, this phi angle, you will get different kind of patterns. So nowadays we call this kind of structure, especially for plasmonic, as meta surfaces. Right? They show actually very unique different properties. We treat this as a compound nanohole structures, essentially because you not only have the big hole, you also have small holes. So they have so-called enhanced optical transmission effect over there. Now, if we change actually, the incident angle, not only just changes the azimuthal angle, right? During the 3 deposition, right? If the incident angle changes from, like, for example, the first incident angle is 10 degrees, second incident angle to 20 degrees, and the third incident angle is 30 degrees, then the shattering length by each individual sphere will be different. Now, if the shattering length is different, essentially, then, for example, if this is my first one, this is my second one, this is my third one, then the shattering hole essentially start to have handless, right? So, for example, this is a AFM, a very nice AFM image. So this is the first deposition. This is a black circle over here. The red circle is second deposition, and the yellow circle is the third deposition. You can see, we have a nice, skewed holes over here. And this skewed hole actually can show that, if I'm using the right-handed circular polarized light and left-handed circular polarized to go through that, they have a difference. So essentially, you have a delta T over here, shows a CD response with such a very simple nanohole structure. This nanohole structure actually can be used to do chiral molecular sensing. They can tell, the molecule, what is the chirality of that molecule, whether it's right-hand or left-hand side, right? And when you actually incident light at a different direction, their response actually totally reversed because this is a planar structures like this. So essentially, if we also can combine different kind of deposition system, not only just using a single source to do the deposition, we can tune the material property. For example, recently we did this silver magnesium fluoride co-deposition. Now we know that the LSPR material can be used as a sensor. And their sensitivity actually is tuned by the real part of their index of refraction, or the dielectric constant. If the dielectric constant slope becomes smaller and smaller, their sensitivity can become better and better, because this is in the denominator over here. So we also know from physics, the so-called effective medium theory, that if I have two materials coming together, their optical property will be determined by both of the material, and also how many A material is in B material, right, over here. So essentially, you can use the composition to tune the real part of the dielectric constant of that. And so if we do the co-deposition of silver and magnesium fluoride is dielectric material, silver is a plasmonic material, we actually can actively tune their composition while we still get the same size of triangle structures over here. And obviously, they have different LSPR, and we do show that, at 90%, they have doubled the sensitivity compared to pure silver structures like that. So I guess that's everything. So I want to show that by combining colloid lithography and glass angle deposition, you can design all kinds of nanostructures, not only just for optical application, probably there's many other applications as well. Obviously, we don't have a facility like here. We only have very simple facilities, so that's, and also, okay, if we can change the polar and azimuthal angle, maybe, okay, the deposition configuration, we can get a lot more out of this deposition. For example, we can even get triangle into a nanohole structures recently, what we have done. So many different ways. That's it. Thank you very much.
Okay. Can I have a question or two with Yiping?
Yes.
You mentioned colloid may form domains,
Yes.
and all the photo shows just like one domain, right? Or it's continuous most of the time?
All the simulation photos I showed obviously is one domain, but when we do the optical measurement, because the beam size we use is like a millimeter size, so it contains multiple domains. So usually we strive to have a very good condition to fabricate single domain structure. We actually published a paper. If we can fabricate a single domain structure with like a centimeter by centimeter square, then we can get a very good optical, much better optical response than if I have multiple domain structures. But the most time, I mean, the student want to do things very quick, so we get multiple domain. But sometimes multiple domain is good. For example, when we do the broadband absorbers, we need multiple domain. I don't want single domain structure. Multiple domain, the smaller the domain size, the better the response. However, if we want to do an optical device like a filter, whatever, a polarizer, we want a single domain structure. That gives us a much better enhanced response.
Mm-hmm. Okay, well, one last question.
Yeah, very quick question. Yeah. So you showed that you're able to use two sources simultaneously.
Yes.
And I'm wondering for the Swiss roll patterning, can you operate both simultaneously from two different angles to achieve?
Yeah, actually, yeah, you have used two different angles, and also you can do the double helical structure. We are working on that. If you do two sources simultaneously, so it's like a DNA double helical DNA structures. Yeah.
Okay, very good. Let's thank Dr. Zhao again.